We are looking at an ideal Rankine cycle, okay, consisting of these four components. We have been provided information about the state at the entrance to the turbine with the state 1, right? The pressure is given. It's mentioned that it's saturated vapor. Same way information about state 3 is given. And it's an ideal Rankine cycle. So we know that the process 1 or 2, which is the expansion within the turbine, it's isentropic. Same way, the compression within the pump is also isentropic. So we know the entropies at state 4 and state 2 simply because we know the entropies at state 1 and 3. All right, so that's enough information for us to go ahead and solve this problem. The other thing that's mentioned is the net power output of the cycle. It's given as 100 megawatt. And for the cycle, we need to determine the thermal efficiency, backwork ratio, mass flow rate of the steam in kilogram per hour, and the thermal efficiency. Now, the first three parts are something that's there in the textbook. The part D is something that I added just to give you a better understanding of how this efficiency business works. All right, so let's look at what we did. Certainly, when you're provided with this sort of a question where you need to go and determine the efficiency, or let's even the work output or heat input or anything like that, you're going to need enthalpies, right? I mean, we need the values for enthalpies to even go ahead solving this problem. And that's what we spent time on Sunday. We looked at how to find different states and then basically get the enthalpies at different states. So enthalpies at state 1 and 3 were very straightforward, right? These are simply Hg at this pressure and Hf at the condenser pressure. And for the other two enthalpies, which is H2 and H4, we had to make use of the fact that the process is isentropic. So we found out the quality for state 2 and then the enthalpy. And similarly for H4, we had to sort of make use of the fact that since it's an isentropic process, it's also a reversible process or an internally reversible process. So we made use of the work input formula for an open system, right? The reversible work input formula, and we equated this to the pump work input, which is basically equal to the difference in the enthalpies. And this is how we found. Okay, so this is a very simple trick that we need to determine H4. It is something that I like to ask in one of the class tests or in quizzes. So make sure you are aware about how to get this pump work input or the enthalpy at state 4. All right. So once all the enthalpies are known, determining or calculating thermal efficiency is rather simple thing, right? It's not a very difficult task now. Thermal efficiency, as we know, is simply a ratio of the net work output of the cycle divided by the heat input of the cycle. Now, when we talk about the net work output, well, we are producing some work output in the turbine, certainly. There's some work out happening, but we need to provide some work input to the pump, right? To pump the work, to pump the liquid, or to pump the water from a pressure of 0.08 bar or 0.008 MPa to 80 bar. Okay, we need to pressurize it. So we need to consider the work input that we need to provide in the pump, and therefore we take the turbine work output minus pump work input divided by the heat input, and that's what gives you the thermal efficiency, right? And we have all the enthalpies here, H1 to H4, and you plug in the numbers. Okay, these are again the only thing here was to determine these enthalpies, right? Once you plug in the numbers, we get an efficiency of 37.1%. Now, considering that most of the practical power plants have efficiency somewhere in the range of 45%, an efficiency of 37% is not a bad efficiency. It's sort of an average thing. Yes, it can be improved, but it's sort of okay. But one thing to consider here is that we're getting a 37.1% efficiency for an ideal Rankine cycle. Okay, we are considering the processes to be isentropic, the expansion and the compression. So this is not always the case. So we'll have to see how we can play around with this number. But for now, 37 is not bad. And this figure simply tells you that out of the heat that we are providing, right, it's telling you how much work we are able to extract out of it. So out of a certain amount of heat input that comes in the process 1 to 4, 37.1 is basically the net work output, right? So turbine work out minus pump work in. So this is reasonable. Okay, reasonably good. And now you may ask what's happening with the rest. Well, the rest is simply being rejected, right, to the surroundings. It's going as q dot out. So this is what's happening in here. All right. So this is the first part is done. Now for the second part, the back work ratio. This is another thing which is very useful. The back work ratio is simply the ratio of pump work input divided by the turbine work output. We're always interested to calculate this because we want to minimize this as much as possible, right? You want to ensure that you're able to, extract as much work, net work from the given power cycle as much as possible. So you want to minimize pump work as much as possible, and you want this ratio to be as small as possible. If back work ratio is very much smaller than 1, that's very good for us. Okay, and we would want to keep it that way. Now here when we plug in the numbers for the work input to the pump divided by the work output from the turbine, these are simply the enthalpies that we already calculated or found from the tables. The back work ratio comes out to be 0.84%, which is less than 1%. Okay, so this is excellent, and this is the case for all vapor power cycles, right? In all vapor power cycles, the work input to compress a liquid, it's pretty small as compared to the work output we get from the turbine. So this is the usual case, and this is one of the reasons why vapor power cycles make a lot of sense. That's why a lot of systems, whether solar thermal, whether it's nuclear, whatever fuel you use to heat up the working fluid, a lot of these systems depend on the Rankine power cycle to generate power, simply because it makes sense from the back work ratio point of view. Remember, this back work ratio of 1% or less than 1% is not always going to be the case for all cycles. When we will go to the Brayton cycle, where you have to compress a gas, you will see that this ratio is about 40% or higher. So it varies from cycle to cycle, right? It depends on what you're doing with the working fluid. But whenever we consider a Rankine cycle or a cycle where you're having where you're compressing a liquid, this ratio is going to be pretty small, and this is one of the advantages of this sort of a cycle. All right, so these two are pretty straightforward. These two are things that we have done before. Now let's move forward and calculate the mass flow rate of the steam. We have been provided the net power output. Okay, it's 100 megawatt. So the question is, how do we go ahead and calculate the mass flow rate? Anyone can give me suggestions?
Energy balance equation.
Okay, so you want me to do energy balance for the entire cycle, or how should we go about it?
Yes, I think.
Okay. Yes, we can do sort of energy balance for the entire cycle, but what we're going to get is, heat in plus work in is equal to heat out plus work out. And well, I know all these numbers per unit mass. I just don't know the mass flow rate. I mean, I could just write it as q dot n by m dot plus blah blah blah, because we don't have the mass flow rate yet, so we can't exactly find q dot n. We can find q dot n by m because it's simply equal to h1 minus h4. So yes, that's a good idea usually, but here it's not going to take us far. Any other suggestions? The network output is given to us, right? What we have calculated till now are turbine work output per unit mass, pump work input per unit mass. It's not very complicated. Well, there's a lot of quietness in the room. So are you guys studying for the quiz, or what's the case? You should have some ideas, right? I mean, I'm perfectly fine if the answer is wrong. It's not, the purpose is to have a discussion here, not just to give right answers, because if you know everything, then we don't need to teach this course, right?
Actually,
Yeah.
Doctor, my mind is busy in the quiz.
Okay. Well, maybe then I should have the quiz in the beginning of the class next time.
It's better, Doctor.
It will be
Okay.
safe, doctor.
Uh, all right, we will do that. The problem, the reason I don't have it in the absolute beginning is because some people will join 1 or 2 minutes late and then they'll complain, oh, I did not have enough time. So, all right, we'll do a poll and we'll move it if that is what you guys want. Because yes, I understand that the quiz will always be on your mind till you actually do it and get whatever marks you have to get. All right, let's try to focus here and try to look at this because your preparation is not going to change in the next 20 minutes. Okay, so we just need to get the mass flow rate. All right, and the turbine work output per unit mass is simply the difference in the enthalpies, which we already calculated. Same way with the pump. Now, when we say the net work output, it's simply the turbine work output minus the pump work input. All right. So you could write it as m dot times WT by m dot or minus WP by m dot, right? Or I mean, this is one way of writing it, or you could just write the work output of the turbine as mass flow rate times H1 minus H2. Okay, same way you could write it for the pump. The key point is that we know this value of net work output. We know these numbers, the work output per unit mass from the pump, which is equal to this difference in the enthalpies, work input per unit mass in the work output per unit mass from the turbine, which is these difference in enthalpies. Same way we know the work input per unit mass in the pump, right? So you just have to sort of divide that. So m dot would simply be the net work output divided by H1 minus H2 minus H4 minus H3. The enthalpy changes within the turbine and within the pump or the compressor. Okay, so it was very simple. It's not very complicated. You just have to know that this m dot here. We just need to determine it. Okay, that's all we're looking for. So we have these different enthalpies from H1 to H4. The net power output is given. It's a matter of plugging in the numbers here. Now this net power output, it was given in megawatt, right? So we need to convert that into kilowatt before we can calculate the mass flow rate, right? Because everything here in terms of enthalpies is in terms of kilojoule per kilogram. So we need to keep the units consistent. Once you do that, this is the mass flow rate that comes out, about 105 kilogram per second. Now I want you to wait for a minute and sit on this number, right? Think about this. 105 kilogram per second, right? So for water, I mean, if it's sort of difficult to think about kilogram, you say 1 kilogram is about the same as 1 liter of water. Okay, so we need to pump about 100 liters of water every second. All right, this is what's needed to keep the power cycle, keep the power plant running. So this is a pretty huge quantity of water that we're talking about, right? So if you think about the 1 liter, sorry, if you think about the water bottle that you get in the supermarket for a real, that's about half a liter, right? 0.5 liters. So you're talking about 200 of such bottles, and so much water needs to be supplied every second. So we're talking about absolutely huge quantities of water. Okay, and this again is not any sort of a random number. This is very close to the flow rates that happens in actual power plants. So if you go to the steam power plants in Jeddah or even the steam power plants that are located in the eastern province, you will see that the flow rates are somewhere in this range. Not exactly 105, but could be maybe 90, could be 120, somewhere in this range, right? So this is a very it's very close to the real numbers that we are dealing with. So in the question, we had to provide the mass flow rate in terms of kilogram per hour. So you just need to multiply by 3,600 to do that, and this is the final quantity that we're talking about. It's absolutely a huge quantity that you're dealing with, right? So it's 3.77 into 10 power 5 liters per hour. So you have to sort of pump in a huge amount of water continuously, and you need to circulate that to generate 100 megawatt power output in this particular case, right? For the temperatures given. So here is where this problem mostly ends. You get the mass flow rate, thermal efficiency, and back work ratio, and you have solved more of it. And if you look at what was asked, the tricky part here was only to get H2 and H4. I would say not the tricky, maybe the slightly involved part. Everything else was very straightforward. Okay, everything else was just a matter of putting in either from the energy balance or using the definitions for enthalpies and back work ratio. Now, we calculated the thermal efficiency of this plant to be 37.1%, but I mean, just relying on energy efficiency is not enough. We need to sort of compare it with the situation for a reversible cycle, because just looking at 37.1, it looks like a low efficiency, right? It doesn't look very good. It looks as though we are wasting the remaining 63%, and it's just going to the environment, which is sort of a waste of exergy, right? So before we come to a more, before we decide whether we can make what changes we need to make to, sort of make this power plant more efficient, it's a good idea to sort of calculate the Carnot efficiency, right? Because Carnot efficiency would be the maximum efficiency for the temperature limits that we're looking at. So when we talk about part D, here we need to calculate the thermal efficiency of a Carnot cycle, which operates between the same temperature limits. So what are the temperature limits that we're looking at? We're looking at this, the Tsat here, okay? This Tsat to be the TH, right? In the boiler, Tsat at the boiler pressure. And we're looking at Tsat at the condenser pressure to be the lower temperature, right? Temperature of the low temperature reservoir. So once we get that from the property table, simply by going to the saturated pressure tables and getting up the values for 0.08 bar and 80 bar, we can plug it into this equation. This is the formula for Carnot efficiency, 1 minus T low by T hot. So at 0.08 bar, 41.5 degrees Celsius is the saturation temperature, and at 80 bar, 295 degrees Celsius is the saturation temperature. Now 295 is sort of reasonably hot. It's not very hot. You could go higher than that, but this is what we have for this particular case. Okay, and as you know, we need to convert the degrees Celsius into Kelvin, so we have this plus 273 here, and when we do the calculation, the Carnot efficiency comes out to be 44.6%. Now this is interesting, right? I mean, this tells you that even if you had the most perfect cycle ever, the efficiency would only be 44.6, or let's say 45%, which again is not so nice, right? I mean, you're talking about wasting 55% of the energy, even in the most ideal scenario. So you got to wonder where that's happening, right? Or you could play around with ways to increase efficiency. Now, when we talk about the efficiency increase in any system, or when you talk about the efficiency increase in any heat engine, as we're going to discuss about with respect to this power cycle, there's only one trick to it, right? One I would say defining trick, and the way to achieve that would be several ways. So one defining trick that you need to do is you need to somehow play with this formula, right? You have 1 minus T low by T hot. So let's say if you want to increase efficiency, you have two options: either decrease T low, right, temperature of the low temperature reservoir, or increase T hot. If you can do either one of these, you're going to increase the efficiency. Okay, so of course the efficiency increase in the Carnot cycle when you play around with the temperatures is not exactly equal to the efficiency increase in the Rankine cycle. It's not going to increase by the same amount, but it is surely going to increase. So this gives you an idea about what to do, right? And so when you look at this Carnot efficiency, it's 44.6%, and we said 37.1% was our efficiency, right, for this particular cycle. So you could also go ahead and calculate the exergetic efficiency just to get an idea about how bad the situation is. And since this is like a heat engine where it converts heat to work, you could use the formula that we discussed in the last, sometime in the last week. So it's thermal efficiency of the cycle divided by the thermal efficiency for the Carnot case, or for the maximum thermal efficiency. And for this case, it comes out to be 83%. So you can see from exergetic efficiency, it's already pretty high. It's not so bad. It's simply bad because we're looking at energy-based efficiency, and this is not giving us a accurate picture of what's happening. All right, questions? Any questions here before we move forward?
Clear.
All right. So, of course, what we were dealing with was an ideal vapor power cycle, and it had isentropic compression and expansion. But in reality, we don't have isentropic compression and expansion, right? There are, of course, irreversibilities involved. The only question is how big are the irreversibilities? Okay. So when we talk about irreversibilities, the main sources of irreversibilities are fluid friction and the heat loss to the surroundings. Fluid friction is a major cause, right? It's a more dominant cause than heat loss to the surroundings. Now, when we talk about a power cycle, or let's say any sort of a power plant that you consider, one of the major irreversibilities or the main irreversibilities occur in the pump and the turbine, and we sort of take that into consideration by defining their isentropic efficiencies, right? So the isentropic efficiency allows you to compare the work input or output for an actual case as compared to an ideal case. An ideal case is basically an isentropic expansion or isentropic compression. Okay, just like we did an example 8.1. That's why the name isentropic efficiencies. Now here, when we are talking about the isentropic efficiency for a pump, the work input for a pump would be higher in an actual case as compared to an ideal case. Therefore, we divide the ideal work input by the actual work input. Okay. On the turbine, however, the actual work output would be smaller than the ideal work output. The ideal work output is the one with the subscript S. So here we sort of divide the actual work output, we keep it at the top, and we divide it by the ideal work output. The reason is we always want to keep efficiency less than or equal to 1. Okay, you don't want it to be higher than 100%. That's how efficiencies are defined. All right. So now you may be wondering, why is this happening? Why is one thing smaller? Why is the other thing higher? Well, it's simply because when in a pump, we need to provide some work input. All right. And when you look at any process where when you're looking at this expansion or compression process where the entropy at the exit of the component is greater than the entropy at the inlet, right? So such as what happens in the pump from 3 to 4, right? Or in the turbine from 1 to 2, right? S2 is greater than S1 or S4 is greater than S3. What we will also notice is that enthalpy at state 4 is actually greater than H4S. H4S is for the isentropic case where the entropy would remain same. Similarly, S2 is greater than S2S. Now, when these enthalpies are greater, they're going to play a role in the work input required. So here, when we talk about H4 being greater than H4S, so since this value is greater, the difference between H4 and S3 is going to be higher. So the actual work input would be greater. That's why we keep it in the bottom, okay, for a pump. Now, when we talk about the turbine, we said S2 is greater than S2S, right? H1 is sort of fixed. So if H2 value is higher, then this difference would be smaller, okay? So again, we keep it at the top because it's a smaller value. The work output is a larger value in the ideal case. That's why we keep it at the bottom. All right. So this is all about isentropic efficiencies. We will just look at how the previous problem would change when you consider some isentropic efficiencies and how the efficiency would go down a bit. Okay. This is the problem. The first problem in your homework also involves isentropic efficiency. So make sure you understand this part. If you have any questions, please ask me right away. All right. So in this example 8.2, we need to reconsider the ideal Rankine cycle that we just did for 8.1. But here we need to consider that the turbine and the pump both have isentropic efficiency of 85%. We just need to determine the thermal efficiency for this new cycle. Okay. So this is the formula for the isentropic efficiency of the turbine. By the way, the formulas are given in the formula sheet. So here, I mean, when we were looking at example 8.1, we were looking at the ideal case. So we already have determined the enthalpy at state 2, but that was for an isentropic case, right? So that's H2S now. So we have the value of isentropic efficiency, all right? We know H1 already, and we in fact know S2S as well. All that we need is S2. So since everything else is known, we can just calculate H2 as H1 minus efficiency, the isentropic efficiency times H1 minus H2S. It is making use of this equation right here. Okay, nothing else. H2S was 1794.8, and when we plug in the numbers, H2 comes out to be 1939. So as I mentioned, H2 is greater than H2S, right? And this is something that you would expect. If H2 comes out to be lower than H2S, then there's a problem in your calculation. So always do a sanity check once you have done some calculation. All right, it should make sense. So for the pump, well, it's sort of a similar scenario. The isentropic efficiency for a pump is the ideal work input by the actual work input, which can also be written in terms of the enthalpies. We already have H4S, okay, but for here, what we could do is we could simply make use of this work input formula. Okay, so we have isentropic efficiency of the pump is equal to the ideal work input, and ideal work input, as we know from before, or a reversible work input, can be written as specific volume times P4 minus P3 and divided by the actual work input. Okay, so we know this value. We know we can calculate the values, or we already know the values for a reversible work input, and from these two we can calculate the actual work input for a pump, and this is simply equal to H4 minus H3. H3 is known, WP is what we calculated just now, so we can get H4 from there. Okay, so this is what we are doing here. We're making use of ideal work input, isentropic efficiency, and calculating the actual work input there. And you plug in the numbers, and this is what it comes out. You can see that the actual work input is 9.48, which is slightly higher than 8 point something we had for the ideal case, right? This part right here. Okay, again here, H4 would be higher than H4S, right? Because this value is simply higher. The difference is not so large, but yes, it's there. And the difference is not so large simply because the work input is pretty small to start off with. All right, so once you have the value, updated value for H4 and H2, we can plug it into this thermal efficiency equation, and this is what we get, 31.4. So we said the thermal efficiency of practical power plants is approaching 45%, but the thermal efficiency that we're having here is 31%. And as you can, and if you notice, it's a huge drop. We had 37.1 in the actual case, but sorry, in the reversible or the ideal case. But when we consider the isentropic efficiencies, it came down to 31%. Okay, so although the isentropic efficiencies here are slightly on the lower end, we have turbines and compressors or turbines and pumps where isentropic efficiencies are sort of reaching 90%, you would say. But certainly, yes, there would be a drop, right? We will not be getting 37% for this case. For an actual case, you would expect somewhere around 31% or slightly higher, and that's not good. Okay, so we have to sort of figure out how we can increase the efficiency. All right, so before we go further, any questions on what we just covered, the isentropic efficiency and how to make use of it? All clear? Okay.
Yes.
All right, so let's just quickly look at the power cycle that we discussed, right? So from second law of thermodynamics, we know that we cannot convert all the heat to work, right? All the Qn that's coming in, it cannot be converted to work. We have to reject something. So there will be some work output or net work output, plus we have to reject some amount of heat to the surroundings. Okay, so when we consider power plants, as I said, we're reaching efficiencies as high as 45%. Now, when you look at any power cycle that you're considering, the thermal efficiency can simply be calculated in this manner, like we just calculated for the 2 cycles. And just because some of you may have confusions about this formula, I want to clarify that this formula applies for both ideal and actual cycles. We are not making any assumption when we're coming up with this formula for the thermal efficiency, right? It's equally valid for both cases, as we just made use of it for the actual case as well. Okay, so now here the key part is how do you increase the efficiency? All right, so the efficiency of a given power cycle can be increased in a couple of ways, and you can rely on the formula for Carnot efficiency to give you hints about how to do that. And again, as we discussed, there are two main ways of doing that. Either you sort of increase the temperature or the average temperature at which heat addition occurs, right? So T4 to T1, during this process, the heat addition is occurring. You play around with properties or stuff in such a way that you increase T hot, or you sort of decrease T low. Figure out ways in which you can reduce the temperature at which heat rejection is occurring, right? Heat rejection occurs during the process 2 to 3. You have to somehow bring this temperature down, and you have to sort of take this temperature up. These are two primary ways of doing that. OK, so this is the basic concept. How you implement that is what we are going to discuss. You can implement this thing in several ways. OK, so when we talk about increasing temperature or decreasing temperature, of course, it's not going to happen by itself. We need to spend some money, change the equipment and so on and so forth. So it's sort of limited by economics as well, how high you can go. But there is also thermodynamic limits, which simply come from the fact that we cannot achieve higher 100% efficiency, right? There will be some heat rejected to the surroundings, so you got to take care of that. So it's a combination of both thermodynamics and economics.